minutes. The floor is yours.
Thank you, Aitan. Thanks to the organizing committee for the work and for the invitation. It's a pleasure to be here. So I'm not working on waves, and it's a long time since I've been working on conservation laws, so I don't really have a topic that fits this conference, but I have a topic that fits the name of Abel in Norway, because what I'm going to tell you is related to, in some way, to the work of this year's Abel Prize winner, Luis Caffarelli. So no waves, on the contrary, something much more elliptic, namely variational regularity theory for the problem of optimal transportation, which I think some of you will know. And in fact, I think this variational regularity theory, which we developed, we means together with Goldman, who was at the time postdoc in Leipzig and now is back in Paris. The advantage of this approach to regularity theory for optimal transportation and the Morgenthau equation becomes apparent if you look at a problem from discrete optimization, the problem of matching, and this is how I'm going to start with. So as I mentioned, the initial collaborator on this was, or is, Goldman. And then for the application to the matching problem, we got support by Martin Huisman, who knew about these types of problems from his PhD thesis. And I will also present kind of the result with a joint PhD student of Martin and myself, Francesco Mattesini. So that's the plan. So here is, so as I said, I'd like to start with the application of this regularity theory, because I think it's quite intuitive and doesn't require much background knowledge, and that's the problem of matching, optimally matching two point clouds. So you're given two point clouds, the green and the blue point clouds in d-dimensional space, and now you want to find they have the same magnitude, and you want to find a pairing between the points so that the sum over the squared distances is minimized. Of course, this is just one of many choices. You might say it might be more natural just to optimize the sum of the distances. Perhaps at the end I will say something about this problem, but let's focus on this problem where you want to minimize the sum of the squared distances. So that's a priori completely combinatorial problem, because in some sense you have to go through all permutations to figure out what's the optimum. But there is one convenient observation, is that this optimality can also be rewritten in what's called cyclical monotonicity between the pairings. That means whenever you take a kind of finite subset of your points, and now you could also take infinite point clouds, and you look at their cyclical permutation, you have to have this inequality. And that's equivalent to optimality and is a good substitute if you're looking at infinitely many point clouds, which I will look into. So that's, you want to cyclically, you want to find a coupling, a pairing that satisfies the cyclical monotonicity property. And in case of a finite point cloud, it's really equivalent to this minimization problem. And now, it has been common in, so this is kind of a combinatorial problem, but at the same time it's also a statistical problem, because it comes up when you sample these points from a common distribution. So you think of two independent sets of samples of the same large magnitude of these of a given distribution. Some people would call it an empirical measure, and you want to, in a certain sense, identify how close are these two empirical measures, these two realizations, and that's a statistical question. And perhaps the simplest way of phrasing it is to take these points from a uniform, spatially uniform distribution, and that gives rise to what's called the Poisson point process, which I will explain a bit more on the next slide. So that's the task which was introduced, I will give you more names later on, in the Hungarian combinatorics school in the 80s by Aitai, Komnos, and Tujnadi. And here is kind of how you should think about the Poisson point process. So there is, in a certain sense, poor man's version how to think about it. Sometimes I like to speak about canonical definitions. So think about, like in Jalal's talk, kind of an artificial large torus, and now you throw in points randomly, independently, with a uniform distribution into this torus, and you throw in as many points so that you have 1 point per volume. So in this case, let's think of L being an integer, and you throw in L to the power d points. So the density is equal to 1, the typical distance between these points is of order 1, but of course occasionally you may have big holes, and occasionally the points may cluster. And in fact, this is something that's kind of classical observation in statistics, or that this object here stabilizes, so you can really send L to infinity, and what you get is kind of a probability measure on locally finite point clouds, and that's called the Poisson point process. And let's say the grown-up characterization of it is not via this limit, but is as follows. Kind of a random, an ensemble of point clouds is the Poisson point process if and only if the following two properties hold. Whenever you're given a set, let's say a finite Lebesgue measure, think of it as being open, then you look at the number of points which fall into the set. That's a random variable. And the first requirement is that this random variable, which has values in the integers, is Poisson distributed with an intensity which is given by the Lebesgue measure of the set. That's number one. And number two is, if you're given two of these sets and they happen to be disjoint, like drawn here, then you have two random variables, let me say n and n prime, or omega and omega prime. And the second postulate is that these two random variables are, statistically speaking, independent. And that's, in a certain sense, the grown-up characterization of the Poisson point process. And here, as I said, we always normalize the intensity to be unity. So again, think of these points as having on average distance 1. Okay, now let's go back to the Poisson point, to this kind of problem of optimally matching two independent realizations of the Poisson point process. And let's think about it at first in one space dimension. It makes sense to think about it first in the simplest case. So, so I have two copies of R, the line, and I have two independent realizations of the Poisson point process, as indicated here. And now I want to match them in an optimal way, in a cyclically monotone way. And now you can see that in the 1D case, this is extremely rigid. In a certain sense, I have just to I have to pick the only degree of freedom I have. I have to pick kind of 2 points which I match. I take them to be close, as here. And then from then on, by cyclical monotonicity, which in one space dimension is just plain monotonicity, everything is determined to the left and to the right. So, so the problem is completely boring in one space dimension. But what you realize is that something is wrong, perhaps at least wrong, with the initial intuition that you want to kind of find close by pairs, because a simple analysis reveals that if you move far out, far away from where you originally kind of made the choice, you will see that the points which you match have a huge distance. And in fact, this distance between the matched points diverges from your original pair like the square root of the distance. So it's, it doesn't work well. This optimal matching doesn't work well. It leads to this type of divergence, at least in the 1D case. So here again is kind of the magic picture you should have in mind. And the reason for this is, of course, that this random point process, this Poisson point process, is is very far from being uniform or hyper-uniform, as some point processes are, in the sense that if you look at density fluctuation, at mesoscopic density fluctuations, they're still pretty large. So if you look at kind of, if you divide up your system into blocks of side length L, then you will find, and then you look at the number of particles in this block, and you look at the density of particles in this, the number density, so you divide the number by the volume of the block, you will find just simple central limit theorem scaling that these fluctuations scale like 1 over the square root of the volume. That's the typical CLT central limit theorem scaling 1 over square root of the number, which here is proportional to the volume. So it's these density fluctuations which lead to that type of strange behavior in the 1D case. But now you see that in a certain sense, in higher dimensions, things are better, because the larger D is, the smaller this number will be at a given test size L. And in fact, there is a simple back of the envelope argument, which you'll find already in kind of the first papers on this, which tells you that the most interesting dimension is the 2-dimensional case. And here's the argument. So it's a thought argument, a Gedanken experiment. So let's say you give yourself kind of a subsystem of side length L, and and you look at let's say the number of green points in this subsystem. So there will not be exactly L to the power D, but as we discussed here, there will be fluctuations. And there will be, sometimes too little, sometimes too much points. Let's think, without loss of generality, too many points of the order of the square root of the volume. So to leading order, you have L to the power D points, but then this number, you have deviations from that order. So you have too many green points. So you have to match, you have to find partners for them, you have to find blue points. And if you want to not see this 1D behavior of kind of having to transport, having to find your partner very far away, if you want to minimize your carbon imprint, so to say, then you should be able to find sufficiently many partners in one neighborhood of your system. And then again, as a simple geometric question, how many points do you have, at least in terms of scaling, to leading order in kind of the one neighborhood of your system? And that's a surface scaling, that's L to the power D minus 1. And now you do the math, as they say in the US. You compare these two numbers and you find that they are the same if D is equal to 2. So it's very clearly this argument tells you that, that D equal to 2 is the critical case. And the question is the two-dimensional case in a certain sense on the bad side or on the good side? Does it behave more like the one-dimensional case, or does it behave like the high-dimensional case? So that's the question which people have looked into, and in order to really pin this question down, I have to introduce one last statistical notion, which is the notion of stationarity or shift covariance. And let's look again at this picture here of the 1D case. So if you look at this matching, I mean, no matter how you choose the first pair, if you look at it from far, you will always see where you started. It will not be statistically stationary. If you look, if you look somewhere else, you will see very biased matchings, either one or the other side. So so it's not kind of there is you will always see a center of the universe if you look at any cyclically or any monotone matching. So you don't want that, because the Poisson point process doesn't have a center of the universe. The Poisson point process is statistically translation invariant. In other words, if you take a point cloud X and you shift it by some deterministic vector Z, and then you look at kind of this random variable, and you look at this random variable, so you look at these two point clouds, then they have the same law under the Poisson point process. So that's a kind of a more adult way of saying that you don't see an origin, or it's statistically stationary. So some people of you may know perhaps the notion of stationarity in time. This is stationarity in space. And then you can ask, well, I mean, so since my two independent copies of the Poisson point process, x and y, have this stationarity property, I want the matching, which after all is a point cloud in the product space. I want the matching to have the same stationarity property. So I'm seeking, in other words, I'm seeking kind of a random point cloud x, y in the product space, so that if I just look at the first component, I get Poisson point process. If I look at the second component, I get Poisson point process. Both of them are independent. The point cloud should be cyclically monotone, and it should have this invariance property, the stationarity. And now the question I want to know, is that possible in 2 dimensions or not? 2 dimensions, again, is the critical dimension, the interesting dimension. And so this type of question, as I mentioned at the very beginning, has quite some tradition. So it came up a long time ago in the Budapest school. But then it was taken up by probability theory. So for instance, Talagrand devoted quite a bit of, more recently Ledoux devoted quite a bit of work. But in a certain sense, for our community, it was interesting that not probably, but I know that people from the Scuola Normale and the physics department in Pisa talked to each other. So Parisi and his group got involved into this problem because there is some kind of mild analogy to spin glasses, and they came up with an interesting connection to PDEs, which I want to explain. And then that was made rigorous by the group around Luigi Ambrosio, Estrade, Trevisan, Glaudo, or a couple of more junior people that worked with Luigi on this. And so here again is the question, so this precise question, was not kind of considered by this group, but in fact it was considered earlier by our collaborator Martin Bussmann and his advisor at the time, PhD advisor Karl Theodor in Bonn, and they proved, in a certain sense, by methods which are a little bit similar to stochastic homogenization, that if you're strictly larger than 2 dimensions, you do have such a stationary and cyclically monotone coupling. And we proved that the 2-dimensional case, you're on the bad side. You don't have it. So the 2-dimensional case, in that sense, behaves like the 1-dimensional case. And in order to prove this, we used very much the philosophy from Parisi's group of connecting that to PDE. So the connection, I will explain the connection now in the sequel. So this was more or less a teaser that from a problem that looks completely combinatorial and statistical, there is an interesting connection to PDE. Okay, and perhaps not so surprisingly, some people will have already guessed it. And anyway, it was in the title. This matching problem, of course, is just a discrete version of the problem of optimal transportation. So kind of optimally coupling 2 probability measures, or 2 measures on the same mass. And here is one slide on the formulation by Kantorovich of the problem which was originally formulated by Goldman. And so you're given two measures, 2 non-negative measures in RD, which could have singular elements, could have smooth Lebesgue densities. Doesn't matter for this formulation. It's important that they have the same mass. And now you want to, as random variables, you want to couple them, which means you want to find a measure on the product space, RD cross RD. So as the language goes, so that its first marginal is given by the first measure, and the second marginal is given by the second measure. That's, in the language of Kantorovich, that's a transference plan or a transfer plan. And so that's a large space. So for instance, the product measure would be in this space, but many other measures. And now what you want to minimize is the infinitesimal cost of transporting mass from one point to the other. And in line with the discrete problem, you look at the square of the Euclidean distance of the initial and the terminal point. So you look at the square, the squared length of the displacement, which is involved in shipping the mass here into that enlevé of Monge. And then sometimes, and we'll do that, this minimum also has a special structure because it's the square of the distance function, and that's called sometimes called the Wasserstein distance. Different names for it. So that's optimal transportation. And now, of course, it's known since a long time that optimal transportation connects to the Monge-Ampère equation, which is kind of very important elliptic, fully nonlinear PE. So here again is the problem of optimal transportation. You, among all admissible transfer plans, you minimize this cost functional. And while I said that the product measure is admissible, the optimizer, in fact, has a thin support. So the optimizer in the product space is supported on a d-dimensional set. So it has codimension d and dimension d. And in fact, it's supported on the subgradient of the convex potential, which comes from the dual formulation. This is a completely convex variational problem. And so in other words, if there is some mild regularity, we know that the gradient of this convex function, which exists almost everywhere, pushes forward the initial measure into the target measure, which I think would be really big. And now if you use the transformation formula on the right-hand side to express this integral differently, you see that this identity here, which has to hold for any test function, for any test observable zeta, turns into what's known the Monge-Ampère equation, which is the statement that you take this convex potential, you look at its Hessian, which is a positive semi-definite matrix, you take its determinant, and that should be equal to mu. That's the Monge-Ampère equation. And that's a kind of famous equation. Here it is again. Because it's, in a certain sense, a very nice example of a fully nonlinear elliptic PDE. So in the sense you can think it's being defined by this function on matrix space, and it's elliptic because it has this, this monotonicity property here. If you take two positive semi-definite matrices which are ordered in the sense of definiteness in this way, then you know that this this function here is ordered, and that means that this equation satisfies a comparison principle. So does, for instance, of course, the Laplace equation, for which this function would be just the trace of A. But it's quite different because it's highly degenerate, because the determinant, in a certain sense, this convexity of the determinant degenerates at the boundary, the ellipticity degenerates at the boundary of your cone of positive definite matrices. But that again is just the reverse of the medal, that this equation, the Monge-Ampère equation, has a much larger invariance group, which is which is the special linear group, which is non-compact, in particular much larger than the invariance group of the Laplace equation. And so Caffarelli's kind of main insight in a very readable and short and crisp paper from '90 is that by means of comparison principle and by means of invariance, of affine invariance, and by some very smart compactness arguments, he showed that Pogorelov's counterexample to regularity is really the only one that can appear. And from then on, 2 years later, he wrote a paper which applies this to optimal transportation and gets certain global regularity statements in optimal transportation. So there are these two completely different ways of getting to the Monge-Ampere equation, either the variational point of view or this maximum or comparison principle based fully nonlinear point of view. And in a certain sense, all the regularity theory, even for the optimal transportation problem, which clearly has variational nature, was ultimately based on Caffarelli's work. And what we came up with is kind of a regularity theory, which I want to tell you a bit about, which completely avoids this this comparison principle and this fully nonlinear way of approaching it. So here comes the very interesting heuristics from the physics paper from Parisi and co-workers. So in fact, it's nicer to explain it not in the case of the fully discrete matching problem, which I introduced at the beginning, but in case of the semi-discrete matching problem, where you match the Poisson point process, so the empirical measure, to the Lebesgue density. So that's perhaps also the statistically more relevant question. And so they were aware that there is a Monge-Ampere equation, and so they were rewriting the Monge-Ampere equation the following way, just by subtracting 1, which is the average density of this point cloud. And then they were realizing that if you look at this random measure and you subtract kind of the background charge, you get something which, roughly speaking, behaves like white noise. In law, on large scales, it should behave like white noise. So that's the first observation. And then they said, well, but white noise is pretty small on large scales. If I average it, if I mollify it with kind of some your favorite mollifier on a large scale r large compared to the typical distance of the particles, which I did set equal to 1, then white noise in fact becomes very small. It decays like the averaging scale to the power minus d over 2. That's again the CLT scale. So therefore they said if one solves the Poisson equation with this white noise right hand side, also the Hessian should be very small on large scales. So in other words, if you add the Hessian, or if you add the solution of this Poisson equation to the quadratic potential, and you use the fact that the linearization of the determinant around the identity is the trace, which is something people in PDE, of course, are quite, in the Monge-Ampere equation, are quite aware of, we know also from other contexts, then you realize that this should give you a pretty good approximation for your nonlinear equation. So in a certain sense, they said, in this matching problem, we are in a situation where, although the measure is very rough, we should be able to linearize. We should be able to show that the Monge-Ampere equation, this highly nonlinear equation, behaves like a linear equation. So they said we expect that the displacement, so grad phi, which is the map under which you push forward the measure mu into the Lebesgue measure minus the identities, that's the displacement, should be well approximated by the gradient of this much simpler problem, of this Poisson problem. So on average, in an average sense. So that's what I wrote down here. And if I have the time at the end, I have 2 numerical slides which really show that this conjecture is very good and true. So it's some kind of large-scale linearization, and that's exactly what. So with Huysman, we were able to prove on the basis of this variational regularity theory with Michael Goldman, and I think that's an application of the regularity theory, which I will present on the 2 slides which are coming, which you could not have done with Caffarelli's regularity theory because this one always requires that the measures have at least a Lebesgue density that's bounded away from 0 to infinity. So here's the statement. So again, what we want to do is we're having an optimal transference plan for some measure mu. Think of coming from the Poisson point process and the Lebesgue measure, and we want to compare it to this solution of the Poisson equation with the difference of the measures on the right-hand side. And the result states that this is indeed true in a kind of large range of situations. What we need to know is that on every scale of observation, so on every ball of radius r around the origin, let's say, balls which are large compared to one being kind of the characteristic scale of the microstructure, if you want. If on every scale r larger than 1, you know that the Wasserstein distance between the given measure mu and the uniform measure is small in a volume average sense, and that this constant is close to 1 in the kind of right dimensions. If you know this, that this happens at a certain rate d of r, then indeed you have that the average displacement is close to the average of the Poisson curve. So indeed, there is this large-scale linearization happening, no matter how rough these measures are. So this is, in a certain sense, a justification of the heuristics of Parisi, which at first looks completely shaky, because you're not at all in a situation where you could do a classical linearization of the Morgan-Ampere equation, because the measure mu is very rough. So that's the kind of one part of the result, and in order to connect to more standard elliptic regularity theory, which you might perhaps be used to or have seen, I want to kind of single out one result which leads up to this large-scale linearization result, and it's an harmonic approximation result. So here is the statement, and I explain it on the next slide again. So again, we're given an optimal plan that connects two measures. Now the second one doesn't have to be the Lebesgue measure. These two measures are completely arbitrary measures. You might think of them as being purely atomic, or whatever combination of atomic and densities you may want. And what we have to do is we have to monitor two quantities, two size measures. We have to monitor a local energy. So that's not the global energy which this guy minimizes, but it's a local energy where we look at all the particles or all the mass which starts in the ball of radius here normalized to 6. 6, of course, is nothing special. It's just larger than 1. And so, which is kind of the mass which starts in the ball of, in the B6 ball or ends in the B6 ball. And then you look at the cost that's attached to that type of transportation. So that's one quantity you have to monitor, local energy. And then, like on the previous slide, a local data size. So in this ball of size B6, you look how close your target measure, your initial measure mu, is to a constant, and how close this constant is to 1. And you do the same thing for the target measure lambda. I didn't write it down because it's exactly the same. And now the statement is very much in the spirit of what's called epsilon regularity or harmonic approximation result. So you give me kind of a small number, a fraction, tau, and I tell you that there exists a universal positive constant which depends on this fraction and on the dimension, and some large constant, epsilon c. So that if I'm in the situation that E plus V are small, so below a threshold epsilon, so we're in kind of in a small size situation, then there exists a harmonic gradient. So the gradient of a function whose Laplace Laplacian is equal to constant, so harmonic gradient, which is controlled such that the displacement in a smaller domain, in half over here, 1/6 of the domain, that the displacement is close to the gradient of this convex function. In this close in the sense that this quantity, which has the same flavor as E itself, in fact is just a fraction of E, this given fraction of E, plus a large constant times the data term. So that's really the core for this entire. I mean, at the core of the results which I told you is really this this type of regularity statement, this type of harmonic approximation statement of showing that you can locally relate this nonlinear and discrete and rough optimal transportation problem to kind of a classical PDE, one of the simplest PDE kind of harmonic functions. So it's again on the next slide, because something which I would like to stress is that kind of all the homogeneities and the metric are natural here. So the energy is a quadratic quantity in the displacement or in the solution. So we have energy on the left and on the right hand side. The squared Wasserstein distance is again something that's quadratic in the solution, or quadratic in the data. So we have d to the power 1 here. So the fact that we have powers 1 here is crucial. So in that sense, it's very reminiscent of something much more standard if you look at kind of a more standard, strictly elliptic but nonlinear PDE, like written down here with the right-hand side, where you would like to show that in the appropriate metric, you can find a harmonic function by solving an appropriate boundary problem that's close to your nonlinear solution, modulo just the local right-hand side and the local size of the solution, which is then something which you use in Campanato theory to develop kind of regularity. So it's very much in the spirit of, let's say, a more standard elliptic regularity theory, but it works in the right with the right homogeneities like here, and in the right metric, and always in this weak metric, in this energy or Wasserstein metric. So that's very important for being able to use it. So I'm only have about 2 or 3 slides more. Perhaps one interesting question is now, how do you get this this harmonic approximation? How do you construct it? And in fact, it's constructed by solving a Neumann, the flux boundary data problem. That's perhaps not so surprising. And so the natural question: what are the flux boundary data? What's the inhomogeneous Neumann boundary data which you have to choose here for your Poisson equation? And for that one, it's convenient to take this particle perspective on optimal transportation. So the fact that you're transporting mass from x to y. So think of x, y being in the support of your optimal transport, and you, in a sense, transporting mass along straight lines. So you're dealing with an ensemble of trajectories x of t, and we're given our ball, let's say of radius r around the origin, and what we have to keep track of in order to find the right Neumann or flux boundary conditions is where trajectories enter and exit this ball. So in fact, first when, so at which time do they first enter and exit the ball, and then what's the distribution of the points at which it enters and exits the ball. And that defines 2 a priori, completely irregular measures on the boundary of the ball. And the difference between entrance and exit measure defines exactly the Neumann boundary data. So that's how you have to define boundary data. And then the right-hand side, which you want to be constant, you just take the difference of the total mass, and then you can check it's easy to check that these 2 data are exactly compatible because you're not losing or gaining mass by looking at these trajectories. And then the important thing is to find, kind of like often in this elliptic regularity theory, to find the right radius. You have to pick a good radius on which you, in a sense, collect or detect these non-boundary data. So there is a kind of optimization of the radius. So just to make this more palpable, on the last slides, I want to show you a numerical simulation. So not surprisingly, that's done for a box instead of a ball, because that's easier from the point of discretization. So, and we're going back to the specific problem of matching two point clouds, two Poisson point clouds in a large box, so red and blue. And now we're looking at kind of not the harmonic approximation, but this more first type of result where you solve the Poisson equation with a non-constant right-hand side. So what you put on the right-hand side is just the difference between the empirical measure, the target empirical measure, so the red points inside the box minus the blue points inside the box. So that's a no-brainer. And but then for the flux boundary condition, you do exactly in a more specific or hands-on way what I explained before. It's already based on the optimal matching. So let's say we have already computed the optimal matching. And so we look at all the particles which are matched across the boundary. So we look at all the kind of matchings inside, and we look at where they cross the boundary. That's what we put here. And for the exit or the other way around, we put that here. And so that's of course rough data, rough measures. I mean, just measures on the right-hand side of your Poisson operator and on the right-hand side of your Neumann boundary data. But in a finite element discretization, that doesn't matter because it's a Galerkin approximation. So we just evaluate this on piecewise, on continuous piecewise linear functions. So this is something you can immediately put onto your use a finite element solver. Of course, you have to, for this you have to solve, you need to solve your combinatorial problem before because you need it in order to get the boundary data. And so here just I hope one sees a little bit. There are just two graphs where we do this for a cube of side length of 75. So that means there are many points inside, well, of the order of 75 squared points inside, and of course there are also points outside. And what you see here, in principle, you should be able to. Well, I'm not sure whether you can see it. So what we look at here is the difference between the solution of the Poisson equation with these inhomogeneous data and the displacement averaged over a small, and here is somewhat larger length scale. So that's our averaging length scale, like in Parisi R. And here, when you do it over just a small length scale, which is not much larger than the typical particle distance, when ideally you would see still a bit of deviation between the green, between the blue and the red error. And if you do more averaging, and you just put one error in the center of each cell where you do the averaging, they're practically identical. So this is not just a theoretical thing, it's really something which you can see in numerical simulations, and eventually one could also think about using this in a hierarchical way of computing this type of matching problem. Okay, I think my time is almost over. So this is one more or less cultural slide. So some people may know the regularity theory for minimal surfaces, so famous program by the Giorgi, which starts, at least on the level of the epsilon regularity, that in order to get some type of flatness implies smoothness argument, what you should do first is you should compare your minimal surface to the graph of a harmonic function with the same boundary data. And so you should construct a competitor based on this graph of the harmonic function, and then you should use kind of convexity of the functional to infer some information. So that's the That's the spirit of the Giorgi, and in kind of the most variational way it was carried out is in an old paper by Schoen and Simon, and there's clearly an analogy. So in minimal surfaces, you approximate by the graph of a harmonic function. In optimal transportation, you approximate the displacement by the gradient of a harmonic function. So same objects. And in both cases, at least in the Schoen and Simon version, you never use the Euler-Lagrange equation. You only use the fact that what you're looking at is minimizing given its own boundary conditions. So you avoid using the Euler-Lagrange equation. In optimal transportation, in this result, we don't. But then you run into certain kind of natural problems which have to do with the fact that in linearizing, in comparing a surface to graph, or in comparing a flux to a displacement, you're changing the type of description. You're not just linearizing the problem, but you're changing the type of description, and that there is a mismatch, and which requires kind of matching the two boundary conditions in the right way, which requires actually in both cases to find a good radius. So there are many parallels in the way, in this variational approach to regularity theory, and in the approach to epsilon regularity for minimal surfaces. And okay, so that's my last slide. So right, so I try to motivate why it could be interesting to develop this kind of completely orthogonal perspective on regularity theory for optimal transportation and more Jean-Pierre. As I mentioned just a second ago, it's really it's in spirit very close to what you do in this mother of all regularity problems, which is the minimal surface problem. I think I would say it's more robust than the maximum principle-based approach because it doesn't require any regularity of the measures, and I think we show that by making the point that it gives you very precise information in case of problems with rough data like the matching problem. And now one can, there are many directions. I mean, that's something which I mentioned at the beginning. Here we looked at the square distance. In a certain sense, much more natural would be the exponent t equal to 1. That seems out of reach, but by connecting to the P Laplace equation, I think we can treat the range between 1 and infinity for this non-existence result, for instance. I think so we want to explore, we're exploring the connection to something which is nowadays quite fashionable in the numerical community, which is called entropic regularization. That's a way of dealing with the optimal transport problem in a softer way by relaxing it somewhat somehow. And I think since we never use a PE, but just the variation principle, our approach is in a good position to give a kind of uniform regularity results also in this case. So let me stop here.
Thank you. Questions? Yes, please.
Can you give a sense of how? Sorry.
That's okay. You can go ahead.
Can you give a sense of how theorem 2 works in different dimensions? How does dimension matter?
In theorem 2, let me see what I call theorem 2 here. So that was this harmonic approximation.
Yeah.
So in this theorem, it doesn't, constants depend on the dimension, but otherwise it doesn't matter.
Okay, so it doesn't basically see.
No, it doesn't, it's oblivious. So a little bit like in, again, minimal surface theory, if you're interested in epsilon regularity, and this is kind of the first step towards epsilon regularity, also in minimal surface theory, you don't see a difference between 7 and 8 dimensions. That comes in later when you're, start classifying singularities, which is something which I think here in the problem of optimal transportation one is far away. So no, short answer, no dependence on dimension.
If instead of Poisson point process, we consider another stationary point process with, let's say, good mixing property, even finite range of dependence, what would be the results?
I think as long as finite range of dependence, it wouldn't. So for instance, for this, so again, this oops. This theorem here is completely deterministic. So here you could take any point cloud. Now for the questions before, like this non-existence question, I think you would get the same result for a finite range process. Things change if you go, if you pass to hyper-uniform processes like Gini-Brie ensembles or so. When you have more uniformity, the scaling of these density fluctuations changes, and then of course that completely changes the story in the sense that there's no reason why 2 dimensions should be critical. But as long as it's finite range, I think that the story would be pretty much the same.
Will it depend on the behavior of mixing coefficient or?
I mean, finite range would be perfectly.
No. I mean, if you have fast decay of mixing, some mixing coefficient.
Okay, no, then certainly I would expect that there is some, you know, I mean, you need in some sense integrable decay, roughly speaking. But now, how this exactly translates into mixing conditions, I haven't checked that. But I mean, roughly, I would say, provided the mixing is strong enough, you should get the same.
Yeah, so exponential mixing would be sufficient.
I'm pretty sure that should be the case.
Okay, thank you.
Any more questions?
So at the end, did I understand you correctly that one future thing could be to look at different p's, and then you would, instead of connecting to harmonic functions, you would connect to p-harmonic functions?
Mm-hmm. Yeah, that's already, I mean, Lukas Koch, who's a postdoc in Leipzig, has already posted out on this result, where here you look at kind of the p cost, and here you would have the power p, and here you would have a p harmonic function. So that works, at least up to this stage, that works the same. And therefore, we're also pretty confident, also, although we didn't write it up yet, the non-existence result would also hold for p strictly between 1 and infinity, but the most interesting case would be p equal to 1, but then as people know, we lose a certain convexity, strict convexity, and then it's not clear.
Okay, I suggest that we close here. Thank you very much.